We now are at the end of the list of the topics that we wanted to cover in the course. This last topic is statistical learning, or the more familiar term for it is machine learning. You may have also heard data science. All of it refer to the same topic, or a similar combination of topics. So what has happened over the past, especially decade, is that we have had a lot of data from all sorts of sensors, thanks to MEMS in a large part. And now we also have a lot of computation power. And also we have all sorts of communications, especially wireless communications. And we have started to try to generate context from what is going on in the environment. This is data-based. We look at the data that is coming to us, and we try to look at the patterns of changes in that data in order to figure out what is going on. We are also applying it to all sorts of social issues, right? So there's, obviously you have heard about, data that is collected from social networks and trying to, let's say, for example, predict the purchasing patterns in a customer, or things like that, the political views of people and things like that. Well, we are not talking about those stuff. We are talking about applications of these new tools that we now have available to us, namely inexpensive and abundant sensors, abundant computation power, and relatively easy communications in order to solve engineering problems. Okay? So what is physics-based sensing or physics-based modeling? And we want to compare it to empirical modeling. Empirical means based on measurements and data. In a physics-based model, you have a model-based approach, a system-based approach. What that means is that, I go and look at the laws of motion, Newton's laws of motion, and I try to predict how an object responds to inputs, noises, all sorts of different parameters. So I have already created a box. I've already created a platform, a framework for how the system may respond. It could be quantum mechanics, it could be fluidics, it could be, circuit theory, whatever it is. I have some laws that govern the behavior of that system. And that laws basically limit what the output possibilities are. However, I need to know about the system, right? To say if I'm looking at an electronic circuit and I want to solve or come up with a model for it, I will, in order to predict the response of that system, let's say if I'm interested in frequency response, I need to go and figure out the poles and zeros of the transfer function for that system. If it is nonlinear, a different set of problems and issues, but again, I need to go and figure all those things out within the framework that I have created at the beginning. These models in most situations are very deterministic and precise, right? So if you, for example, follow, well, let's go back to that electronic circuit theory. The behavior of an electronic circuit, you have the resistor values, you have the transistor parameters, you go and bias the device and you get this much voltage at the output. It's 5.32. You know what it is. And if it is not that, it's because of some random variation in your system. Sometimes you can take some of those variations into account and figure out, what is the range of possible values for the output. But in most cases, it is deterministic. It gives you a single value. And they're very precise, meaning that there's no noise. You usually don't have a range of values for that output or for the parameter of interest. To do this stuff, to create these physics-based models, well, you have to be a physicist or an engineer. You have to have knowledge of interferences, things that can come and show up at the output of your system, especially, for example, in electronics. Signals can be capacitively or inductively coupled onto your signal line, and they will show up at the same time as your signal. So where did they come from? How do I account for them? Nonlinearities are big deals, right? If I go and design the system based on a linear approach, and let's say the changes at the input are larger than what I assumed, the nonlinearities can mess up what I predicted for the output of the system quite a bit. Couplings between different systems and also different segments of a system. So it can be fairly complicated, and that's why engineers have good jobs, because they're good at doing this kind of work. Now, what we said is that over the past few years, we have these data-driven models. So this is where you look at the data and how the data is changing, or the patterns of changing the data in response to the inputs, and you try to come up with a relationship that basically replicates that behavior. If you apply the same input to it, you get the same output. In these cases, in most situations, you do not create that framework that we had for physics-based models, right? So in this case, in most situations, you have the same function, and you basically apply it to everything that you have. This function, therefore, must be quite flexible, right? So you have to have a lot of knobs to turn in order for it to, let's say, mimic a linear behavior versus a nonlinear behavior, and all sorts of different things that come into here. But you basically are creating a black box. The input goes in, the output comes from the other end. The goal of data-driven models is to basically come up with a function, and that function may not have a closed form that replicates the performance of your original system. What you do is that you apply some inputs to the original system, look at the outputs, and try to replicate that behavior or learn from that data in order to do the same thing on new inputs. Now, because it's only about data, because it's only about actual measurements, you applied some input and you're measuring some output, you do not know what is going in here. You do not also know what is coming and affecting the performance of this system. So let's say you may have interference. Let's say, again, if you think about an electronic circuit, the output stage may get hot. The heat from that stage can go back and affect the performance of the, let's say, input amplifier that you had. It's not really that easy to model that physically. But your data-driven model can actually, without even knowing about it, can take that into account. That unmodeled complexity shows up in data. You apply some input, the output is changing. Well, the heat that you produce in the power amplifier at the output stage also is going to affect the performance of your circuit. It affects the data, and your black box, the model that you will be creating from this data, will not know any of that, but it can, if done properly, take them into account. It can associate, create, let's say, it can model those kinds of issues that maybe we didn't even take into account or didn't consider at the beginning, or we decided not to model because they were too complex. Data-driven models, therefore, are very, very flexible and can be applied to all sorts of problems. And, it's a, let's say, advantage of them as well as disadvantage. So if you do not do it properly, you can apply the wrong statistical model to a problem, get really nice looking results on paper, on your computer screen, and then if you take it to the field, it fails miserably. You have to be careful. At the end of the story, it's always good to have some physics-based models, some physical understanding of how things are going to happen, especially in engineering situations. And make sure that your data-based model, data-driven model, is staying within bounds, right? So it's not all of a sudden producing data that is just physically impossible. So what is the sequence of steps in a machine learning problem, in a statistical learning problem? The first thing to do is to identify the problem. What is it that you want to improve with data, with capturing and keeping the data? It could be, in this picture, do I have a human? So that's a problem. Or it could be, is this room at this point of time comfortable to be in or not? Right? So in that comfortable level or comfort level can be assessed through a combination of, let's say, different parameters. It could be temperature is probably one of the more important ones, but at the same time, relative humidity is very important too, right? So you can probably live with a little bit of higher temperatures if the relative humidity is lower, right? But if both of them are high or both of them are low, then you basically are going to be outside the comfort zone of most people. But you do not want to set thresholds, right? So you can, and I think a lot of the old AC systems would do that. But nowadays, maybe you want to come up with a set of conditions that their combination is comfortable, right? And a lot of these smart thermostats nowadays are doing that. So figure out what the problem is, what the variable is that is going to tell you, whatever objective that you want to achieve. And the next thing to do is that you need to go and collect the data. To collect the data, you need to instrument your data sources. What does that mean? Well, if you need to measure temperature and humidity, well, you have to have a temperature sensor and you have to have a humidity sensor. That's as simple as that. And then you start collecting data. So in the beginning, for data-driven models, you cannot start from scratch. You have to create some boundaries for that black box model. So the way to do that is that you go and collect some data from the field, feed them through the main system, look at the output. Somebody goes and decides, if this is comfortable or not, for example, for the room condition example. And you have this set of data. Then you bring that data to your model. And once you collected and stored that data, you need to usually go and clean it up, right? So you have to integrate it over time. You don't want to respond to changes that are happening every 10th of a second. You need to transform it sometimes for easier classification. If you want, sometimes you can get rid of some unwanted issues in your data. It could be the drift. It could be the effect of, let's say, day and night on your measurements, things like that, right? So you need to prepare the data for your model. Then you build the model. This is where you go and learn from this data. You try to pick a function and adjust the variable parameters that you have in that function so that it maps the input data to the outputs that you are interested in. So that will be the next step, build the model. But once you build the model, you have to make sure that it works well, right? So again, this is all virtual. This is all based on numbers and computations and graphs and things that are in our head or in a computer's CPU. You have to make sure this is working well. You have to go and evaluate the model. Ideally, we would like to show new data to your system and see how it behaves. In practice, that's not always possible. So what you do is that once you have data, once you collect the data, and somebody went through the trouble of labeling it, you keep a portion of that data, use some of it for training your model, for learning from the data, for adjusting the function parameters, and then treat that last bit of the data that your system hasn't seen as new data. So you feed it into your system and look at how it responds. Ideally, you want the responses to match the labeled outputs. Practically, there is always a bit of a difference, and then we'll talk about that soon. And then once you have enough faith in your model, then you want to use it or send out the results, right? Now, these machine learning functions or statistical learning algorithms, in most cases, do not use raw data. In most cases, I'm not interested in the temperature of this room at any given point. I'm interested in the comfort level, right? So if I look at my smartwatch, I'm not interested in knowing the acceleration value, and I actually need to know all the 3 axes at any given point of time. I want to know if the user is walking or standing or sleeping or running, right? And raw data doesn't really help me. If I know the 3 axis acceleration values here, it doesn't really tell me much about what is going on. So what I do is that instead of processing raw data, I go and extract features. A feature summarizes the useful information in your data, right? So for example, it is no, well, it is the mean value of your acceleration data, for example. It could be the number of spikes per second in your acceleration data. It's something that you go and calculate from the raw data that you had at the input, but now that calculation, that measurement simplifies, extracting meaningful information from it. So for example, if I go and look at that acceleration data and I look at the spikes in acceleration that can correspond to me, walking, the steps that I take, if I go and calculate the number of those spikes in acceleration per, let's say, 10-second windows. So if it is like 10 or less, I'm probably walking slowly. If it is 20 or more, maybe I'm running relatively, let's say, modestly. And if it is, 30 or more, maybe I'm running with small, short steps, but at high speeds, things like that, right? And if it is less than 2 per 10 seconds or less than 1 per second, per 10 seconds, I'm mostly stationary. But that number of spikes per 10 seconds is just one number. How do I calculate it? I get the raw data. So I may be sampling that acceleration at, let's say, 20 hertz per second. Per 10 seconds, I have 200 samples. For 3 axes, that's 600 data points. I look at all of that, do the processing on it, and come up with one number. It's the number of spikes per 10-second window or 5-second window. So things like that are called features. So a feature is an individual measurable or calculable property or characteristic of something that we are observing. And it helps us distinguish between different activities, different regions, basically helps us figure out or build context from sensor data. So let's go through some examples. I have a list of outcomes for my machine learning algorithm or statistical learning algorithm, and I'd like you to think about useful features here. So for example, estimation of house prices in a region. What are the useful features that you can use in order to estimate the price of a new house on that block, in a block. So examples include, the area of the house, the width of the house, how wide it is across the street, the depth of the house. If it is super narrow and, let's say long, that really doesn't help. Nobody likes that kind of a building. Another feature could be the number of rooms in that house. Another feature could be the age of the building. Another feature could be, well, actually, most importantly, especially in Vancouver, is the area, postal code, right? All these things come into play. So these are all features that collectively, let's say a realtor can look at them and come up with an estimate for a house price that you want to put up for sale in a new area. Or you can basically use to figure out if the price for that house is a fair value or not. So how do we detect or predict faults in machinery? So just think about features. What could be your data sources and what could be the features that you extract from that data? And maybe pause the video after each one of these steps so that you have a second or two to think about. But okay, so examples could be vibration levels. It could be noise levels, sound. Noise in this case is acoustic sound. Those things could tell you if your machine is operating properly or not. Activity detection from a sensor data could be in your mobile phone or in your smartwatch or anything else that you're carrying. So think about activity in this case, let's say, difference between running and sleeping and standing and walking and all that. And maybe even, take it a bit further. Some of these smartwatches are designed for active people so they can distinguish between biking or swimming or running or working with weights or playing different types of games. So what would you do in that case? What are the signals that you would capture and what are the features that you would extract from those signals? I would say, one obvious example is an accelerometer that you can use. Automated detection of zip codes from handwritten addresses, right? So this was actually this is a classic example in machine learning that people, when they write numbers, and especially, let's say in the US, it's a 5-digit number that determines the zip code. In Canada, we have a combination of numbers and letters. But if somebody has to read each one of these, it obviously takes a lot of time depending on the number of mail. But this is something that could be left to machines. And if a machine is reading that handwritten address, they need to figure out what the zip code is. And how do you do that? People write, let's say, zeros in many different ways, or twos in many different ways. And how do you know if it is a 2 or not? And then, what you do is that you go and look at a lot of zeros that were written by different people, a lot of ones that were written by different people, and you try to come up with an algorithm that distinguishes between a 0 and a 1 and a 2 and all these other digits. And then you have to test it. But think about that. So you have, let's say, a pixelated image, let's say 10 pixels by 10 pixels or 20 pixels by 20 pixels, image of a digit. What could be the features that will tell you a 0 apart from a 1? And then what could be the features that could help you figure out if this is a 1 or a 7? And what about 8 and 0? And what about 2 and 3? Things like that, right? So you as a human can think about features, and this is usually the best thing to do, especially in the engineering applications, that you have to engineer the features. You have to figure out what those features are. There are ways that machines can go and figure out what features are in your data. They can go and try a whole combination of variables here and go and try so many different features, let's say 1,000 features, and then come up with the first top 10 or top 20 of those features that are going to help you with the problem that you have. That requires a lot of computation. It may detach you from the real world. It may detach you from the physical world. And in engineering applications, the danger with that is that as soon as that happens, you may not really know how your algorithm is working. And remember, in engineering applications, you may be dealing with lives of people. It's not about showing you the wrong advertisement, right? So let's say you do not need shoes, but you see an advertisement for a shoe. It could be a machine or a car that is misbehaving under a tricky, let's say, navigation problem. Or if you think about automatic self-driving cars, it could be a car that missed the stop sign and just went into the junction. And those things are basically literally matters of life and death. So I recommend it, and I think always, to all people that are doing a statistical learning and machine learning and engineering applications, to have a physics-based model in your head. It doesn't have to be too accurate. To know what are probably going to be your best features, and go and try them and build a model based on the features that you can come up with. And then add more if you need to. But you have to have a full grasp on the model and the features that go into your model. So here is the same thing. So I can leave this task to a machine. I can leave the task of feature selection for determining, let's say, handwritten codes to a machine, and they can go and try millions of features and come up with the list of top 100, and I will have extremely high levels of accuracy there. I may not be able to figure out some of them or see how some of them work. It might be okay, right? So it could be just a letter that was not delivered, or somebody had to check the address later on. But I would really be careful in engineering applications in letting the machines decide what features to use. Here is another example, spam email classification. So how do you know if an email is a spam or not? It's a 0-1 question. It's either a spam or not. So how does your email program know that, or your email server? What could be the features that you can use in order to classify an email as a spam? Examples include, you look for certain words, right? So if there is a word Viagra in that email, there is a very, very high likelihood that it's not a legitimate email. It could be, but the likelihood that it may be spam is higher. If there are spelling errors, actually, so some of the ways that in the early days, people to identify spam, they came up with this dictionary of terms that spam email used, and they used that to identify emails as spam or not. Well, the spammers were smart, so what they did is that they started to misspell the words, those target words. So they would insert a number instead of a letter in that word. So let's say I for I or L, they could just put a 1. And it looked the same to a human reader, to a machine. That was an entirely different thing. So it could just go through the filters. A dictionary is not enough. Dictionary of these terms is not enough. So what else can you use to figure out with more higher certainty if this is a spam email or not? Tons of features, right? So think about potential features. So feature extraction is going and extracting or calculating features based on your raw data. Feature transformation is taking the features that you calculated and usually through a nonlinear transformation take them to a state that is easier for your machine learning algorithm to recognize the pattern and classify. So, for example, if my data comes in Cartesian coordinates, but everything depends on the distance to the origin or a certain location in space, maybe I want to take the x and y and present it as in cylindrical coordinates. That is a nonlinear transformation, but now I have one number that should probably make my life a bit easier when I look at the classification. Feature selection is removing unnecessary features. So this should not be a common practice for engineers. You should have a set of go-to features. You should have some features that you've designed or decided on because of the physics of the problem. But sometimes you go and see that my accuracy is 85% now in predicting such and such phenomenon. And if I go and add some, let's say, linear combinations or permutations of these features, I can go from 85% to 95%. So 10% improvement, which is significant in any application. But in that process, you may be producing a whole bunch of features that are irrelevant, right? So for example, how do you go and get rid of those irrelevant features? Let's say if you think about the house price, you go and provide the width of the house, the depth of the house, and the area of the house, right? So the area may not be provided as an independent variable, but it's a feature that you can calculate, the width times depth, let's say in a simple rectangular situation. So it's a new feature that you calculated based on the product of two other features. That's good. But you may also go and produce, let's say, WH cubed and WH squared and W squared H, all those other features. And it is very likely that they may not really help your algorithm that much. So you get rid of those permutations. So how do we do that? Feature selection. Usually it is, again, your engineering intuition and insights should be the first to tell you which features are probably need to be avoided. But there are formal ways of doing it as well. You actually go and look at the effect of each feature on the output of your system, and you rank them based on their importance, how much information each one of them is carrying, and you get rid of the ones that are not that important. You have to define a level of importance, and then you choose on that. So that can be done by a machine, but again, as I said, in engineering applications, you want the human there until we basically, unless you have so much data that gives you enough confidence to do so. But in most engineering applications, labeled data is not really that plentiful. Common features that you use from raw data is, the average of the data. Median actually turns out to be a better feature than mean in many situations. The middle point of your data, 50% more, 50% less. That turns out to be a better feature for a lot of classification examples. Not always, but keep that in mind. You can calculate the average. You can also look at the median. Power of a signal is relatively easily calculated. So, sorry about that. Standard deviation is an indication of variance in your signal. It's the amount of information in your signal, and you want to basically, in some cases, see how much that feature is giving you information. The larger that variance, the larger than standard deviation, the more information there is. Spectral components are important, right? For example, when we talked about activity detection based on the number of acceleration peaks in time domain, you can think about it in frequency domain. How many high frequency peaks I have in frequency domain. If I have high frequency peaks, it means running. If I have low frequency peaks, it means walking. If I have no peaks, it means standing. Spectral slope is important. These are all sorts of things. So especially in acoustic signal processing, for example, spectral slope is important. How does the signal power changes over the frequency spectrum? Now, you go and create these features from your data. So you create a vector that has all this data in it. And what you do is that you go and normally set the first element in that feature vector to 1. This is to account for biases, for offsets in your outputs, right? So it happens a lot that a 0 input doesn't get you 0 output. You get some DC value at the output. That's engineering, right? And that 1 in your feature vector is going to account for the biases, the offsets, the DC values at the output with 0 input in your models. So in most cases, we have that in your statistical model, in your feature vector. There are some special situations where you don't. And we talk about one special case later on. But in most cases, when we talk about feature vector, the first element is usually just a 1, and then the rest are calculated from or measured from your data. Now, when we say learning from data, well, there are usually 2 different mechanisms or topics that we consider. The first one is supervised learning. So what is supervised learning? Well, you look at the system, you look at the input that goes into the system, and you look at the output that comes from that system. You capture both. And what you do next is that you go and pick a function, and you say, I'm hoping that y, the output, is a function of x. X is your input, x is where all the features are, and y is your desired output. So you're hoping that you can find a function that is flexible. You can adjust a bunch of different parameters on it. And you want to learn f. You want to figure out those parameters of your function using the data that you already know produces such and such output. So you have the output. You go and apply the input to your function. You look at the output from your function. If it is different from the desired output, you have to go and adjust some parameters in your function. This is called supervised learning, right? So you supervise what f does to your input and produces an output. And if f is not doing a good job, you go and change some of the parameters there. So sample problems here. Regression. You have seen this in your statistics course, but regression is where we are trying to predict a continuous variable based on some set of inputs, right? So one example, again, could be the house prices. If I want to, the house price, let's say the dollar value to the cent is a continuous variable. I want to calculate or estimate what the price of this house is going to be based on those important information that I have in front of me. Another type of a problem that we can address with supervised learning is classification, right? So you show a picture to a system and there is a cat or not in that picture, and your system tells you, was there a cat in that system or not? In self-driving cars, you show the system is capturing video images continuously. is there a passenger, or sorry, is there a pedestrian nearby that you have to worry, you have to monitor, or maybe if it is the person is in front of your car and you want to stop. Yes or no, is there a person? Did you miss a stop sign or not? Or, is that sign a stop sign or not? You don't know if you missed it or not. Usually, the machine is basically blind to those kinds of issues once you have the model. But you see a sign, you identify a sign, is it a stop sign or not? Classification, right? So it is a yes-no question. Or what kind of a sign is it? One of the few. On the other hand, we can have unsupervised learning. So in unsupervised learning, you have some data, and in most cases, you really do not have an output. You just have a set of data, and these data there seems to be some sort of a pattern in the data. You want to come up with a function, and in both cases, when we talk about supervised or unsupervised learning, the function may not have a closed form. So anyway, you want to come up with a function that simplifies your data, captures what is going on in your data. So for example, two cases are clustering. You go and see for example, when you look at the news page on, let's say, Google, they have put them in these different news items in different categories. There's sports news, there's world news, there's economic news, and there are news that they basically try to tailor to your interests and all that. How do they do that? Well, they look at all the news items that are out there, and then let's say if you see a lot of the repetition of, let's say, the word tennis in a news article, then maybe it is about news. It is about tennis, and then I would like to categorize it as a sports news and maybe subcategory tennis, things like that, right? But initially you really do not know. So which word is repeating and how to clump these things together, you really don't know. You don't have a model for that data. You're just trying to come up with a simpler way of representing that data. So for example, what are the top 20 topics on Twitter? Or you're looking at handwritten documents or ancient writing samples, and you're trying to figure out how many letters were in that language that we know nothing about. Was it 10? Was it 20? Based on these handwritten documents or clay writings that we found. So things like that, right? So we really do not have enough information at the beginning. We try to see if there is some pattern in the data that helps us simplify that data. Another application for unsupervised learning is in dimensionality reduction, right? So you go and see what is going on in your data. Maybe there is a variable that is changing two things at the same time. So maybe we can get rid of those two variables and represent everything with one. And this is essentially factor analysis. So in terms of techniques or algorithms that I'm sure some of you have heard about, supervised learning algorithms. The first one is linear regression. This is something that I'm sure you've seen. I'm hoping that you remember from your statistics course. We go over that quickly in this course, but it's the foundation for, I think, all of these machine learning applications. A lot of the terminology that we use later on is based on what we can learn and simply understand in linear regression. Linear regression is intuitive. Right? So we can actually make sense to it, let's say, relate to it relatively easily. Once we learn about that, we go and talk about logistic regression. Well, it looks very similar, but it's an entirely different situation. This is a classification algorithm. We talk about that. A classification algorithm that is very simple to understand is KNN, K nearest neighbors. Very, very simple to understand and actually works quite well in most situations. We'll talk about that in the it's one of the algorithms that we will cover. Naive Bayes, again, is one of those intuitive algorithms that the good engineers should basically have a good feeling about it already, good understanding about it already, and we just see how we can implement it and then apply it to some engineering applications. Then we get into some regions where machines start to do stuff that may not be that clear to us as humans. And these are some of the algorithms that actually they can outperform anything that we talked about so far. But how they do it is a little bit opaque. You do not really know how the machine does this or that in all situations. You just trust the machine. I normally would advise against using these kinds of algorithms in situations that are critical. But if accuracy is important to you and the outcome is not really going to be too damaging if it is wrong, or if you make a false positive, false positive or false negative prediction, then it's okay. You can go and use these algorithms like support vector machines that are excellent in separating the data into different classes. We go and talk about decision trees. Again, the training part is a little bit tricky, but the nice thing about decision tree is that it's logical. A human brain can follow how the system, a machine is doing it. Actually, these two should have swapped. I would put decision trees up with the other algorithms that are easy to understand. Support vector machines come after that. And neural networks are another set of tools that you can use, very, very powerful, but then again, you may not be able to follow how the machine is doing its job. And for that reason, again, if you're using them, use them with caution. Know that they come, the accuracy, the 3% extra accuracy that you get with a neural network or a support vector machine comes with a significant level of basically not knowing how the machine is doing its job. Issues that we have is measuring model quality. Usually you need data for that, so how do we get the data that you need? Overfitting is a common problem, especially for those algorithms that are a little bit opaque. Neural network, you have a lot of degrees of freedom to set up your neural network, or your support vector machine, you have a ton of options to set it up. And if you do it, it's going to perfectly match the data that you already have. You can get 0% error if you want on the data that you have, but you take it to the field and expose it to new data, and all of a sudden it goes out of whack. It overfits to your training data. And cross-validation, again, is a kind of a similar situation here. It depends on the data that you have. How do you do the assessment of the performance of the algorithm that you're putting together? For unsupervised learning, you have two major groups, two major algorithms. It's clustering one, factor analysis is the other. So factor analysis is about figuring out what is redundant, what is not giving you new information in your, let's say, set of data, and then you can probably just remove some of them, basically come up with a reduced set of data points. Clustering is where you go and look at your data set and just basically identify portions of the, let's say, a feature space where some elements fit in. I will provide some examples of all of these in later slides, later lectures. The challenge here for unsupervised learning is measuring the model quality. If you don't know, if you don't have a starting point to figure out, for example, if you don't know how many letters are in a language that you have, let's say, handwritten samples of it, how do you assess the performance of your algorithm at the end of the story? So because you have less to begin with, less knowledge about the system to begin with, it can be trickier to assess the performance later on. So what is the difference between regression and classification? We have already used these terms. So regression is where the output value or variable of your process takes continuous values. Essentially lots of the sensing parameter problems that are going on around you. The house prices was another example. Right? So it is a continuous variable. It could be any value based on the input parameters. In classification, however, you have limited possibilities for the output. You have class labels. It's this or not, 0 or 1, yes or no, or class A, class B, class C. You know, this is digit that I just, let's say, put into my system. It's either a 0 or a 1 or a 2 or a 3 or all the way to 9. It could not be anything else. So there are 10 possibilities for the output. In many cases, you know, the simplest cases are binary. It's either yes or no, 0 or 1. And you can expand actually those binary systems to go and look at multi-class classification. But, you know, is this a 0 or not? So that could be the first problem. The second problem is this a 1 or not? The third problem is this a 2 or not? Or you can put together a problem such that it gives you, you know, basically the class output right away. So it belongs to class 3 or class 4 or class 8 or class 0, right? So regression is about continuous variables, things that can take any value. Classification, you know, as the name says, you have classes for the output. Now, let's go through some definitions here. We assume that we have collected data and extracted features from that data. We have m separate samples. Each sample, for the input, we have all the features in vector x, and the corresponding output is y. Y could be a continuous variable in regression or a class label, let's say 0, 1, 2, or just 0, 1 in classification applications. But each sample is made of these, right? So we have already labeled or identified what the right output should be. This is data that we have collected. Then my feature vector is an n plus 1 by 1 vector. Normally we set the first element here to 1, and then we calculate n features from the raw data. So I put all of that into a vector form as shown here. The input data set, you know, all the things that went in my system, I can represent it with a matrix by just putting these vectors, transposing them and putting them one at the top of the other. So by the way, this is going to be m by n plus 1. So n plus 1 for each vector, and then I have m of them. So that's my entire input data set. Yi is the true output, the measured output for that sample I, and I can put all of those yi's in a vector if I want to, right? So that vector y represents all of the outputs for those corresponding inputs. So therefore, it's going to be an m by 1 vector, right? So I had m samples, m outputs. And again, these y's could be continuous variables or labels. Now, I define a weight vector as shown here. So W, that is going from W naught to Wn. What I'm going to do is that I'm going to combine the features from my x vector with different weights and create a function of those, right? So there's going to be one weight per feature. All those weights are essentially the variables that I have to control the function. I feed x into this function, and by modifying the weights, my hope is that the output of that function is going to be what I measured, right? So f could be a linear or nonlinear function of features and weights. We'll look at some of these in the following slides. And then to evaluate the performance of my function at the end of the story, you know, I have this function, I'm playing with all these knobs. I want to know if it is doing a better job or not. I have to define a cost function. So a cost function, what it is that it looks at, okay, set the values for W. And you set, you know, something for W0 to Wn, n plus 1 vector. And now you want to see how your function behaves. So you go and calculate the output for all of your inputs. Based on those weights, you subtract or compare somehow the true output from the predicted output, right? So you have the true output that you already measured and know, and the predicted output is what your function is telling you at this point. And if there is a difference, you want to make sure that you take it into account. Ideally, you want that difference to go to 0. But the cost function is going to still go and say, okay, for these values of W0 to Wn, this is your cost function. I compared all the outputs with each other, and this is my collective, let's say, just a number that I tell you in terms of how well your function did. We'll see that the choice of this cost function is very, very critical, and it actually determines essentially how fast your algorithm can learn from the data. And remember again that your function f may not have a closed form, right? So, and this makes it a little bit tricky in some cases where you want to know how the system is doing its job, but you cannot see the function. You just have to try or trust on the input-output relationship. Now, the process of training is to go and play with those parameters, those weights that you had for the function, until you get the smallest cost function, until the difference between the predicted values and the true values is as little as it can be. How do we know if our algorithm is doing a good job? Well, you have a training set and a validation set. So what I would normally want to do, or I would hope to do, is that I would use all of my data to train my algorithm, fix those weights as best as I can, and then take it to the field and start using it. But of course, this is risky. You do not really know how your algorithm responds to new data in the field. So in order to, let's say, simulate the response of my sensor, simulate the response of my model to new data, what I do is that the label data that I captured in the beginning, let's say 1,000 data points, I keep a fraction of it, let's say 200 of it, away. I don't show it to my function. I do not use it. And I take the other 800 and train my algorithm based on that. Now, this is my training data set. Once I have the function here, I show that data that it has never seen to this point to my algorithm. I pass them through my algorithm, and I compare the output of my algorithm with the output that I already know again, right? So I know that that input should produce that output in real world. This is a trained algorithm. How does it do on the test data? I call it test data. So you have training data and your test data, but usually they are coming from the same data set, right? So you basically have some data. You have to keep a portion of it for testing and a portion of it for training. And this is called the validation or cross-validation. So what I do is that I separate the input data into a training set and then later a validation set. The validation set is my simulated test data. It's a data that my algorithm hasn't seen. I train with training set, test with the validation set. Normally, the ratio between the training set and validation set, how much of data you use for training, how much of it for testing, is somewhere between 60 to 40, all the way to maybe 80 to 20, depending on how much data you have and then how much experience you have with those cases. If you have a lot of data, you obviously can afford to save more of it for testing. Remember, it doesn't really well, it matters, but it's not as important what your algorithm does to your training data, right? That's really not that critical. The critical point for you, if you want to use that algorithm, is that how it performs on data that it hasn't seen. So if you have a lot of data points, enough to set all the parameters in your function, go ahead and keep as much of that data as you can for testing your algorithm later on. But sometimes, and in most situations, you do not really have that much freedom. You have a limited set of data available to you. You want to use as much of it as you can to set your weights as best as you can. And then basically maybe you need to go to the 80 to 20 ratio for your training versus validation data sets. Now, as we just mentioned, you have a training set and a data test set. So let's just look at these two situations. Training error is the error that you have, the value of the cost function on the data that you're using to train the algorithm, to set the algorithm, to set those weights in your function. Test error is the value of the cost function for the data that it hasn't seen. You already know the output, so you have something to compare it against compare the output of the algorithm against the true value, but your algorithm is not going to change its weights based on this new data. It is set, it's only responding. So as you increase the number of samples, and J, let's say, is your cost function, what you should expect is that your training error should go up, right? So basically think about it this way. If you train your algorithm with just one data point, well, the error will be 0. If you have 2 data points, again, the error could be 0 or very close to 0. But as you increase the data points in your training set, you start to get some deviations from, let's say, the estimated output and the true output. So the training error slowly rises with the number of samples that you have in your training set. At the same time, hopefully it will saturate, right? So we'll talk about why it may not saturate, why it may not plateau, but it should do that. After you feed it enough data, your algorithm enough data, it should plateau and it should have a, let's say, maximum level that it is approaching to it. On the other hand, for the test data, well, initially you have set the function based on, let's say, one data point, so your function matches that data point perfectly, but if you show it another data point, it probably is going to produce a large error. So what happens with the test error is that initially your data, your cost function may be quite large, so you may start with a high error for new data when you train your function with a small number of data points here. But as you increase the number of data points for your training set, you will notice that your function actually performs better for the data that it hasn't seen before as well. Because that data follows the same pattern, right? So if you set those weights properly, yes, your training error may go up, but the important parameter is the test error, and that will start to drop. And the goal of training is to minimize the cost function. So this is what you calculate. This is the cost function that you calculate. And this is the cost function that you calculate to evaluate the performance. You want to minimize this as much as you can. You must minimize the test error cost function as much as you can. Now, an issue that comes up quite a bit, and we'll see it in the future slides quickly, is the issue of bias versus variance. Does your model have enough variables in it so that it can fit to the data well or not? If your model has too few parameters, let's say you have a data set that comes from a cubic function, but you're trying to fit a line to it, just 2 variables, but you need at least, let's say, 4, then it is said to be a model that is underfitting the data. It has trouble even with the training data, right? And this is called to be a bias problem. On the other hand, you may choose a model to have way too many parameters. And let's say for that quadratic or cubic function, you may choose a polynomial of order 10. Well, in that case, you will see that your function fits the training data really well, but it has a hard time working in real life when you show new data to it. It overfits the existing data. So if you look at the model complexity and think about it as like the order of the polynomial that you're trying to choose to fit to a set of data, the cost function goes down with training error. As you increase the model complexity, your function fits to your training data better and better and better and better. You basically have more options to go through more points. When you show it to the test data, well, different things happen. First of all, the error is a bit higher because your function hasn't seen that data. It probably produces a little bit more error. But it follows the same pattern initially. The test data, when you increase the model complexity, the cost function goes down. However, at some point, you start to overfit to that data, and the cost function value starts to increase. So even though you're doing better and better on your training set, the actual parameter that you have to worry about is the performance on the test set. And in this case, we have high variance for that case. Basically your model is too flexible. It's fitting to everything in your training data, but then misses the information in your new data. And the left of this line is where you have high bias. Ideally, you want to be around here. Your model complexity should be just right.